Hey everybody, welcome back. This video is in many ways a continuation of chatting about the buoyant force. We're going to see how that relates to things floating and sinking. Also, it has to do with something known as Archimedes' principle, so we'll chat about those things. To be honest, before we get into either of those two things, we have to chat about an idea known as displacement, which is important for fluids, for objects in liquids or gases. We already learned the definition for displacement before, a change in position. And there are some parallels, some similarities. We're looking at a change, but technically we're looking at the volume displacement. And this might be review. If you've taken chemistry or maybe just a past physical science class, you may have learned this. When you have an object, you can't have that object and another object occupying the same space in the same time. There's kind of a general universal rule about that. Like you have your hand, your fist, and maybe there's a table in front of you. You can have your hand on the table. Heck, if you're strong enough, you can even punch a hole in the table and your hand can occupy the hole that you made. But what you can't have your hand and the table both occupying the same space at the same time. It's not possible. We can't really have things welded together like that, interlaced like that. So what that means is, let's say I have an object, and on this image on the right, I have like this bolt, okay? Let's say I wanted to find the volume of this bolt, and it's an irregularly shaped object. There's no easy equation in geometry to find the volume, but if you have classic chemistry gear, a graduated cylinder, which measures volume, if you have a starting volume of water, okay, whatever that is in milliliters, if you put the bolt inside, well, because you can't have both bolt and water, the water gets pushed out of the way. We say the water is displaced. How much it has to get pushed out of the way? Well, it gets pushed out of the way the amount of the bolt. So, look right here, comparing these two, the water rose a little bit. This difference, notice there's that symbol, that change in. The change in volume, that must mean the change in the bolt, or I'm sorry, the volume of the bolt is that volume. We say that's the displacement of the fluid. Likewise, very similar idea. Here there's a picture of a pitcher of water. It's filled up to the brim, and we're lowering some object. I don't know what the object is, but it's being lowered. Again, because two objects can't occupy the same space at the same time, some of the water is being pushed out of the way. And if it's being filled right up to the brim originally, that water is going to spill over. We could collect that water, and that would be the displaced water. Okay, so when you're adding an object to a fluid, some of that water, that's going to be our main topic, is going to get pushed out of the way. All right, Archimedes' principle. There's a history to Archimedes' principle. Admittedly, team, I'm not really going to get into it. You can Google it. There's this guy who was a philosopher, ancient Greek, needed to find the volume of an irregularly shaped crown, tried to find the weight to see if it was really solid gold. Not important. But there is a principle associated with his idea. And the first part is something we already learned. Look at this first part. An object in a fluid feels an upwards buoyant force. We already learned that, team. That was the last video. Technically, we did parts of Archimedes' principle before. And here's a copy of that derivation. This is what the buoyant force, due to a difference in pressure, this is what the upward force that acts on all objects in a fluid is. But to be honest, I'm more interested right now in this second part. The buoyant force, it says that it's equal to the weight of the displaced fluid. Huh? That's a weird thing, and something that I did not mention in the last video. So let's talk about that. This second part here. The buoyant force apparently is equal to the weight of the displaced fluid. In order to do that, I have the equation for buoyant force here. It's written down. The buoyant force is equal, if you remember, it's the density of the fluid. It's not the density of the object. The volume that we're dealing with. This is a little weird. I know it's easy just to jump to the volume of the cube, and in some situations, that's not wrong. But if you remember, everybody, we got this definition for the buoyant force really by looking at the level of the water. The H came from the depth of the water. The pressure came from the area that the force of the water was being pushed onto. Is it related to the object? Absolutely. But if we're being technical, the volume has to do with how much water is being pushed out of the way. So that's how I label it. This is the classic way it's labeled on these equations. It's the volume of the displaced fluid multiplied by G. Quick reminders, team. Density is mass over volume, so the mass of an object can be rewritten as density times V. So here I have density times V. This is equal to the mass of the fluid, I'm just going to write F, times the volume of that displaced fluid. Imagine like how much water was here originally before it got pushed out of the way. My apologies, team. Because density times volume is mass, density and volume, I can just replace those with m. Okay, I deleted that v. So right there, mass of the fluid multiplied by the gravitational constant, that's equal to the weight of the fluid. Ignore my chicken scratch handwriting. Oh, okay. So we do in fact see this. Now, does this make conceptual sense? And it does. And let me show you a way to think about it. Again, I have a diagram right here, and there's that equation for buoyant force, okay? What am I doing? Everybody, again, if I have some object, I don't know, maybe this is some trapezoid, some bar of gold maybe, looks like it has a weight of 7 pounds. If I place it in the fluid, we know there's an upward buoyant force. That's what I drew in red. That's what they labeled here. This is saying the buoyant force is 3 pounds, okay? It's going to be based on the density of the water, how much volume gets pushed out of the way, and g. Well, here the water container was filled right up to the brim. And so when we lowered the trapezoid, some water was displaced. It got pushed out of the way. And if you happen to weigh that water according to Archimedes' principle, it's equal to the upward buoyant force. So if we calculated the buoyant force was 3 pounds, what we would see if we weighed the water, if you notice the difference here, if you looked at the difference in this scale, kind of measuring the overall force being pulled downwards, it's equal to the weight of the displaced fluid. Now, why does that make sense conceptually? Before the trapezoid was there, before water got pushed out of the way, obviously there was water occupying that spot. I'm going to try to draw kind of an outline of before the trapezoid was placed in. I know it's the water, so it's kind of weird to talk about, but there was water right there. And if you think of a container of water, normally, unless something weird is happening, that water isn't like accelerating upwards or downwards, nothing like that. So this water must be supported. This water does in fact have its own weight, and if it's not sloshing up or down, there is also a support force. That support force must be balanced to the weight. So the weight of the water in this case was 3 pounds. If that water wasn't accelerating downwards, the upward force must have been 3 pounds. That's the conceptual explanation. All right, team, one more bit of math, and then we're just going to look at some conceptual examples. There's this classic adage that says whether or not things float or sink has to do with the density. Where does that come from? Where does this idea of density come from? To do that, we're going to set up Newton's second law, and I've already kind of done some steps to save a little time. Let's say I have an object suspended. You don't always have to have an object floating at the top or sinking below. Heck, there are some boba drinks that have some floating gels that are kind of suspended in the liquid, so it's possible. So let's say I have this cube, just for the sake of simplicity. We'll start it off by saying it's just staying suspended in the water, not rising up, not falling down. It's in equilibrium, okay? Well, there's two forces. Hopefully by now you know there's weight and there's buoyant force. If I set up the sum of the forces, this is what I have. So I have the buoyant force, which remember is rho times v times g. I'm just going to swing the weight over, and remember weight is equal to mass times gravity, m times g. Remember, what is the density here? This is the density of the fluid. V is the volume of the displaced fluid. And also, team, over here I have some reminders. Mass is density times volume. So I'm going to flip back over to white. Over here, this is for the object, right? This is the mass of the cube multiplied by g, or the density of the cube times the volume of the cube multiplied by g. And all of a sudden, oh man, a whole bunch of stuff cancels. G cancels out. Oops, over here, and it cancels from this side. In this case, since the object is totally underwater, the volume that got displaced is the volume of the cube. So that goes away. And look what I have. The density of the fluid is equal to the density of the cube. When these two densities are the same, the object isn't going to be accelerating upwards or downwards. This is where this density describing things floating or sinking comes from. I'm going to be honest, team, I really dislike this idea. This is a poor or a cheap or a shortcut kind of way to explain what's going on. And I'll kind of prove it to you, I think, with a couple of examples. Like, why on earth is it density that's determining whether or not things are rising to the top or staying at rest or sinking down below? We never used density before. We know in this class what makes objects float or accelerate or stay at rest. It has to do with the forces. That's what's determining whether or not things accelerate, if there's an overall net force on things. this idea of talking about the density, admittedly, maybe I can't get too upset because it's not anything wrong that you're saying, but let me show you some examples of how all of a sudden you trying to use density to explain floating or sinking very quickly breaks down, or at the very least needs a lot more detail. Here I have a picture that's representing Play-Doh. Play-Doh has a greater density than water. It does, period. You put a ball of Play-Doh in water, it sinks to the bottom. There is more weight force than there is buoyant force on the Play-Doh. So when you put it in the water, you let go, it accelerates down. But you form that Play-Doh into a boat kind of shape, maybe a shape like this, then all of a sudden you're able to have a buoyant force that matches that weight, even though the density of the Play-Doh didn't change. So using this, oh yeah, Play-Doh floats because it's less dense, that's not true at all. It's now floating because you increase the volume of the displaced liquid. That increases the buoyant force to match the weight. Another example, we build ships, whether they're battleships or cruise ships or even rowboats, we often build them out of metal. Metal is way more dense than water, period. So you using this adage should say that all metal ships should sink. But obviously we design them so they don't. And then, people are like, well, I mean, okay, Thrasher, but it's like the average density. Oh, well, you didn't mention average density. And the average density of what? You gotta start incorporating the air and how much air is below the surface. It's a whole mess. What determines whether things are accelerating up or sinking down or staying at rest? It's the net force. It's Newton's second law. It's inertia. I would highly recommend you avoid kind of focusing on density as the rationale, because best case scenario, you're almost certainly going to be giving a very incomplete explanation in my class. Maybe you wouldn't get 0 points on a quiz or something, but depending on what they're asking, if they're asking why does an object float, saying it's because the density is not a complete explanation. Okay. Let's just see some more of this idea of buoyant force in action. We know that the buoyant force has to do with how much volume is being displaced. So, when something is floating at the top, it's because it's pushing away enough water to increase the buoyant force. These objects all have kind of the same idea here. We have buoyant force up and weight down. If you lower a piece of wood into water, it's going to start going down and down until it pushes enough water out of the way so that the buoyant force gets bigger and bigger and bigger, enough so it balances the weight. Put an elephant on top, same thing. Now we need that buoyant force to get even bigger because now the weight got way bigger. So you got to push more water out of the way. The classic, swimming pool activity. You have a ball, a volleyball, a beach ball, beach volleyballs, water polo. They have very little weight, but of course they have pretty big volume. Sorry, man, I can't draw a vertical line. Small weight, but big volume means when you hold them under the water, there's a giant buoyant force. So what do you do when you let go? It accelerates. This is Newton's second law. I don't need to use the words density here. Okay, there are net forces on these objects. Well, what about when an object sinks? Again, team, we always have these two forces for objects here on Earth. We have weight and we have the buoyant force. The buoyant force is based on how much water you are able to push out of the way. Well, let's take a rock. A rock has a pretty big weight. Well, rocks are usually fairly compact for their size. Maybe, very simply, their volume isn't big enough. And you can't easily deform a rock like you can Play-Doh. If you can't push enough water out of the way, well, you're going to have more downward force. So the sum of the forces, we're going to have that buoyant force minus the weight equals ma. If upwards is positive, well, weight is going to be greater, so the object's going to accelerate down. So whether or not things are sinking or floating or staying suspended, accelerating upwards, it's a comparison between the buoyant force and the weight. And the buoyant force is based on how much water you can push out of the way. My last slide and my last little question. Team, air is a fluid. And yes, everybody, air has weight. I know that's not the most intuitive thing, but think about it. We have an atmosphere. What's keeping all the air, the nitrogen, the oxygen, the carbon dioxide, all the other stuff? What's keeping the air here on planet Earth? It's gravity holding down the air. So absolutely, air has weight. Well, if you fill a balloon up with just regular air with your breath, it sinks. It doesn't rise up. But with helium, it floats up. what do you think you can conclude? What are some things you can say about this helium balloon? I know it's an open-ended question, but if we think of the force diagram for this balloon, there's weight for the balloon. It's very small, but it has some weight, and there's a buoyant force. For helium, it must be able to push, in this case, enough air out of the way to have a larger buoyant force than the weight force. So the net force on a helium balloon is upward. So you let go of a helium balloon, it starts accelerating upwards. When balloons get higher and higher because of a lack of pressure, they expand even more. So the buoyant force can actually change in liquids or in fluids depending on situations. But team, air or gases, that's also fluid. Water is, of course, a fluid. All these things, there are buoyant forces. Even you standing on the ground right now, you have a buoyant force. Why? Because you are pushing some air out of the way. Admittedly, team, this is probably the only time we're even going to think about the buoyant force that's acting on you, because classically it's just so much smaller than all the other forces acting on us. Weight is significantly 100 times larger at least. Normal force is way larger. Air is very low density. We're not pushing that much out of the way, and we're pretty heavy beings. So technically, all of our past examples, we should have been including the buoyant force unless a College Board question, or at least a question for me, is explicitly asking about like an object in a fluid, or asking about, or seeming like it's asking about buoyant force. Team, you can just ignore it. Nobody is losing points on my exams because they're not drawing the buoyant force that, yes, technically acts on us. It's just negligible. It's so teeny tiny. Okay? But when you're being asked about things in containers of liquids, or obviously it's asking about pressure and stuff, then maybe you should be thinking about buoyant forces. Okay. Oh man, kind of a long video. Sorry about that. I'm done talking. Thanks a lot for listening. See you later.